Methanol is an important industrial chemical used in fuel, solvents, and chemical production. In this project, we designed a complete methanol production system consisting of two main sections, the reactor system and the separation system. The reactor produces crude methanol, but it contains impurities such as water and unreacted gas. So a purification step is required to achieve the industrial standard of 99.5 methanol purity.
So, hello everyone, my name is Isati. So, for our project, we have selected the steam methane reforming SMR route for methanol production. So, as shown in the process flow diagram on the right, our system is divided into two primary stages, which is the syngas generation and the methanol synthesis. So, the process begins in the reformer, where the methane and steam are reacted at high pressure, specifically between zero point 0.1 to zero point 0.6 megapascal, and temperatures ranging from 150 to 350 degrees Celsius. So we utilize a copper-based lead-zinc catalyst here to facilitate the conversion of methane into syngas, which is a mixture of hydrogen, carbon monoxide, and carbon dioxide. So there are two critical reactions occurring in this stage. So first, the main reaction, SMR. Methane reacts with steam to produce carbon monoxide and hydrogen. So CH4 plus H2O producing CO plus 3H2. And the side reaction, the water gas shift reaction, where carbon monoxide reacts with more steam to produce CO2 and additional hydrogen. So CO plus H2O producing CO2 plus H2. So our simulation in symmetry confirms this reaction. In the reformer section, we observed a significant increase in hydrogen mole fraction from 0.407 to 0.471 and the generation of CO up to 0.021, proving that both the SMR and WGS reaction are highly active. Following the reformer, the syngas passes through a separation unit and a shift reactor to optimize the H2 to CO-CO2 ratio before being compressed for the methanol synthesis stage in the plug flow reactor PFR. Moving on to the justification for why we chose this specific route over emerging alternatives like the CO2-based route, our decision was based on four key pillars. First, technology maturity. SMR is a decades-old, well-established industrial standard. By choosing this route, we significantly reduce technical risks because the kinetics and operational parameters are well documented in literature, as seen in the models by Graf and Froment that we used for our copper, zinc oxide, aluminum oxide catalyst. Second, feedstock availability. This project is conceptually based in Bintulu, Sarawak, which is Malaysia's primary hub for natural gas. Utilizing an abundant local resource ensures a stable, cost-effective supply chain for the plant. Third, high efficiency. Our simulation results provided concrete evidence of the road's performance. We achieved a 99.9% conversion of methane in the reformer. This near-complete conversion validates that the technology is highly efficient in utilizing methane resources and minimizing waste. Furthermore, in the PFR synthesis stage, we saw a complete consumption of carbon monoxide, leading to a final methanol yield of 90.4%. Finally, thermal integration and lower risk. While SMR is an endothermic reaction, the overall plant is thermally efficient because we can recover the exothermic heat from the methanol synthesis reactor to preheat our feed streams, compared to CO2 roads, which are still maturing and require complex hydrogen generation systems. This conventional road offers the most pragmatic, reliable, and justifiable design for current industrial applications in Malaysia.
My name is Aisha. I'm going to explain about reaction engineering part. So, for this setup is widely used in industry because it provides high efficiency and supports the exothermic reactions involved in methanol synthesis. The reactor is designed as a multi-stage adiabatic system, meaning the reaction occurs in stage with cooling in between. This helps control the temperature rise due to the exothermic nature of the reaction and prevents catalyst deactivation. So for the reaction kinetics, based on Arrhenius type rate expression, for the main reaction, the value for pre-exponential factor is 1.07 times 10 to the power of 7, and for the side reaction, the value for pre-exponential factor is 1.09 times 10 to the power of 6. After discussion, my team decided to finalize reactor operating condition, which is for the temperature range is operates between 200 and 300 Celsius, for the pressure from 50 to 100 bar, and lastly for the cooling method, we utilize effective quench cooling technique.
My name is Ian. So following Aisha's explanation, I'll be explaining about the Reactor performance matrix, which basically means I'll be explaining about our Reactor system performance. So our Reactor system performance shows a impressive efficiency and output of our Reactor system because it achieved complete carbon monoxide conversion, significant carbon dioxide conversion, and an impressive methanol yield, which further proof that our design is very effective. So the carbon monoxide conversion is 100%, which is complete conversion. Carbon dioxide conversion is 4.28%. Hydrogen conversion is 9.08%. Methanol yield is 90.4%, and the production is 49.9 kilomole per hour.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hafizuddin and I'm going to present 3.1 and 3.2. So for 3.1, the reactor effluent composition and concentration. For the reactor effluents, we can take this straight away from the simulation from symmetry. So it is shown that the vapor fraction is 0.99, the temperature is 150 degrees Celsius, the pressure is 1600 kilopascal, total mole flow of 2228.34 kilomole per hour. And for the composition, we have methanol with fraction of 0.21, hydrogen 0.44, carbon dioxide 0.055, carbon monoxide 0, water 0.28, and methane 0.0003. And to find the concentrations, it is actually very simple. We just need to divide the molar flow rate with the volumetric flow rate. And both of these values are already given uh, from the simulation in the symmetry. So for example, to find the concentration of methanol, we can just divide its molar flow rate, which is 474.33, with the volumetric flow rate 4674.461, which will give us the value of 0.10147 kilomole per meter cube, or also the same value in mole per dm cube. And we can apply these steps of calculation to the rest of the species, and we will be able to get the concentration for each of them respectively. So for 3.2, our proposed absorption-based purification system is require a continuous fixed bed adsorption configuration, which use a packed column to process the crude methanol that run through it with a selective adsorbent material inside the packed bed. So the the adsorbent material will first capture the water and impurity when the liquid flow through it, and this process is operates under liquid phase at moderate temperature and pressure, which provides stable absorption performance together with reduced methanol loss. So this process also use dual column adsorption system that provide a necessary framework to maintain the continuous system operation. What this means is we use one column to do the adsorption while the second column will perform regenerations. So for example, okay, when the first column are doing the adsorptions and all the adsorbents have already reached their maximum saturation points, maximum capacity, the second column will do will perform regenerations, and for the regenerations we also use temperature swing method, which heat the adsorbent to remove the already captured impurities and recover the ability to adsorb again. So by doing this dual system, it's actually helping us to operate the operations to make sure it's run continuously in alternating cycle, which that can help to maintain our product quality at the same level.
The adsorption process operates under specific conditions to ensure efficient separation. The temperature is set at 150 degrees Celsius, which is a compromise between maintaining adsorption performance and avoiding additional cooling costs. The pressure is 1600 kilopascal, which helps increase the driving force for adsorption. Under these conditions, the adsorbent, especially xylitol 3A, can effectively remove water from the methanol stream. These conditions ensure stable operation while maintaining high purity. The selection of the adsorbent is critical to achieving high purification efficiency. The main adsorbent used is xylitol 3A because of its strong selectivity toward water and its ability to exclude methanol due to pore size difference. Silica gel is used as a pre-treatment layer to remove bulk moisture and protect the main adsorbent. Activated carbon is included as an optional layer to remove trace organic impurities. These layered configuration improve efficiency and extend the lifetime of the adsorbent.
Next, require adsorbent amount calculation. To do the calculation, most of the data we obtain from the symmetry software, such as water composition at inlet, total mass flow rate at inlet, initial water mass, water composition at outlet, and the data that need to do the calculation. Unless for the water adsorbent per adsorbent. This data we got from the research that we had done, and we obtained that 0.2 kilogram water adsorbent per kilogram adsorbent. So we do the calculation and we obtain that mass that need is 1365 kilogram adsorbent.
To maintain continuous operation, the adsorption system uses a regeneration process known as temperature swing adsorption, or TSA. In this process, the saturated adsorbent is heated using hot nitrogen gas at temperature between 150 and 300 degrees Celsius. This removes the adsorbed water from the pores of the adsorbent. After desorption, the column is cooled down to around 25 to 40 degrees Celsius to restore adsorption capacity. The system uses two columns, one for adsorption and one for regeneration, allowing continuous operation without interruption. In conclusion, the proposed system successfully integrates both the reactor and separation process. The adsorption system effectively removes water and impurities, achieving high required 99.5% methanol purity. The selected adsorbents and operating conditions ensure high efficiency and stability. Overall, the design is technically feasible and aligns with the industrial process. Thank you very much.